My computer response is becoming slower and slower every day. I can't see your thumbs up, but if you're able to see the screen, just say yes.
Yes, sir.
All right, thank you. Okay, so as we continue with our electrochemistry, we also need to know that there are some processes that will happen naturally. Some of them may be distracted.
Yes.
Some of them may be important. One case in point we have is corrosion. Corrosion is actually a natural process that occurs when conditions when the right conditions are in place, and this happens to be an electrochemical reaction. It involves oxidation, reduction of substances involved when the conditions are right. So basically, corrosion is a gradual distraction, and we're using the word distraction because it's an undesired process. In most cases, it's an undesired natural process that brings about deterioration of metals due to chemical or electrochemical reactions, their environment. So usually, I'm trying to just going to get this. Okay. 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 So one biggest example of corrosion is rusting, and I'm sure all of us have come have seen an example of this process called rusting, and not just here, but I'm sure you've heard of rusting. You've discussed rusting probably in preschool, in primary school, kindergarten, and so on and so forth, and so many places. And what we were interested in really is to identify the redox reaction that happens, and processes like redox reaction, they are very difficult to control, but we want to see how science comes in to protect destruction of a process that may deteriorate and weaken our infrastructure, which are highly depend on the metal framework. And really the process of rusting is an attempt for these metals to return back to their natural state, which is the ore. Because you might want to know that most of these metals, especially that are reactive, we had to extract them from their ores for us to have a pure substance, okay, which is used in many different situations, construction, electricity, and so on and so forth. And when we talk about construction, we're not just talking about building, we're talking about automobiles and ships and everything else. And really, if the use is of that importance and we really don't want this corrosion to happen, okay? Now, this process mostly involves oxidation of the metal. And our metal of interest something that you've looked at, or something that you have witnessed, or something that you're familiar with, is that of the corrosion of iron, or the rusting of iron. So rusting is a form of corrosion that occurs when iron reacts with oxygen and water to form hydrated iron, which is known as rust. So at least you know that rust is hydrated, and how many molecules of water are present is something that you can determine, or something that can be dependent upon the amount present at that particular time. But of course, in the formation, this is a chemical substance, so it's going to hold particular amount of water, and probably the rest of it will just evaporate away. So for this rusting to occur, we're focusing on iron. Now, the focus on iron doesn't take away the fact that other metals can also undergo corrosion. Okay, we are giving iron as an example because it's something that is widely observable and widely affects human activities, or it inconveniences human activity, because iron is widely used. It's cheaper, so it's strong. It finds a lot of use in construction industry. So it's the one we're going to focusing on. But nevertheless, other metals can also undergo corrosion. So what happens, what is discussed here, can also be transferred to other metals depending on different conditions. So one of those conditions is the presence of moisture itself. Now, it doesn't necessarily mean that a material has to be immersed in water. Even just the moisture, the water vapor that comes from any source, could be from plants, from the ground, from the water bodies, as long as it finds its way on the surface of this metal, in this particular case iron, it provides that condition necessary for rusting to. And oxygen, it's everywhere, it's in the air. So when these two are present, and they are easily present, because when you wake up in the morning, you probably find metallic surfaces moist, okay? And oxygen is in the air. So it's something that is an ongoing natural process that really you can't avoid unless you choose to prevent. So below here is the chemical equation that shows what really happens during that process. So we have iron here, we have oxygen, and we have an unknown amount of water molecules that are giving hydrated iron oxide. So the water molecule is indicated with an X, because at this point we don't want to say how much water is present, but at least we know it is part of this whole compound. And basically, this is the formula of rust. Now, you might recall that iron comes from iron oxide, and basically, iron is attempting to go back to its natural state, which is the iron ore. Or at least there's a stage during the purification where you have where you obtain the iron ore as iron oxide. So you usually when this is formed, you will notice the reddish brown substances or particles on the surface of the metal. Then you begin to know that, or you know that rust has been formed. By the time you begin to see the reddish brown substance on the surface, probably it would have reached an advanced, because these are just small particles at atomic level reacting with oxygen at atomic level, at molecular level, and forming this small invisible molecule. So by the time you see the reddish brown substance, it would have reached quite an advanced stage. And what was at molecular level now becomes visible. So the electrochemical nature of corrosion. So corrosion is an electrochemical process involving oxidation and reduction. So at the anode, you're going to have iron. Like I said, we are focusing on iron and just see how iron corrode. So iron, just admit a few. So iron undergoes oxidation at the anode. So iron loses electrons, 2 electrons in this particular case, and remains ion positive charged 2 plus. Whereas at the cathode, the oxygen is gained. Okay, oxygen gains electrons in the presence of water. So water acts more like a media through which these ions or electrons will flow through. Okay, and what is happening is that ion will dissolve, and when it dissolves, since it's in ionic form, it becomes more like an aqueous solution. And in the solution, we have this ion, we have the electrons, and this transfer of electrons in the water, and these meet the oxygen that is present in the air that has come to the surface of the reaction, and oxygen gains these electrons in the presence of water, and they form the hydroxide ions. So the ion reacts further to form rust. So these are the initial reactions. Now, when you are asked to demonstrate or to give a full reaction that will lead to the formation of rust itself, there is that equation that you have been given, but also there is what is happening at the anode and at the cathode. So these are the two reactions. There is this oxidation, there is this reduction. Oxidation in the sense that electrons are being given out, and what remains is the ion. And on the other hand, at the cathode, the electrons are being added, or they're being obtained, or they're being gained to form hydroxide. So now we have two ions, the hydroxide ions, the ions, but the reaction doesn't stop here. This is just the electrode reaction, the anodic reaction, the cathodic reaction, but the overall reaction eventually ends in hydrated iron oxide, which is rust. Okay. So this is just the pictorial presentation of what we are talking about. So we have water droplet there, and we have ion dissolving, forming a pit. So you can see what was a smooth surface now is beginning to form, due to lack of a better term, potholes. Okay, and on the other hand, the surface begins to swell with rust, the brown substance you are seeing there. Okay, so and what is happening at the two electrodes, we have at the anode, like I mentioned earlier, ion losing electrons, and the cathode, the oxygen gaining electrons, and in the presence of water, they are forming the hydroxide ion. So you need to know how to balance this, because you've seen how many electrons are being involved. So you will know where to balance to have a total number of electrons suitable in both cases, the anodic reaction and the cathodic reaction. So don't forget that whenever you see a mismatch in the electrons, try and balance the electrons. It's very, very important to migrate to the overall chemical reaction. Okay. My case is lost. Where is it? All right, it's here. So factors that are affecting corrosion. So we have the rate of corrosion increasing due to the presence of water. That's obvious. Not just water as in flowing water, but also moisture is also water. Moisture is even better at that level, because at molecular level, and the moment it begins to slowly settle on the surface of that particular metal, ion in this particular case, then the presence of oxygen also contributes to this increased rate of corrosion. Then we also have the presence of water. So salt water increases conductivity. This is a well-known fact, because salt water contains these ions. If you are using sodium chloride, you have sodium ions and we have chloride ions. So these will be able to conduct electricity, and that conductivity also increases the rate at which corrosion occurs. Okay, so and an example that can be given is in coastal areas where those constructions or any materials that involve iron, you experience a faster rate of rusting. So the coastal areas, first of all, there's high presence of moisture and the salt water. So the splashings reaching out to these surfaces, we will see a rapid increase in corrosion. Okay. Also, acids, acidic environment increases corrosion rate for obvious reason, because the acidic environment also increases this high rate of conductivity of electricity. So definitely you are going to have increased redox reaction, just as we saw in a battery some few days ago. So impurities also in metal. So during extraction, the aim is to ensure as much as possible to have a very pure substance, because these are the dangers of producing a substance that is not pure. So the presence of an impurity creates tiny electrochemical cells And whenever there's that potential difference between the main metal ion in this particular case and that impurity, whenever the potential difference exists, the electrons begins to flow and oxidation will happen and corrosion will occur. So the presence of impurities also brings about increased rate of corrosion of the particular metal ion in this particular case. Also, high temperature, we all know that reactivity increases with temperature. So higher temperature generally increases corrosion. Okay?
There's a question.
Go ahead.
Can we say a salt or salts act as a catalyst to this so-called corrosion?
Or you're asking if the salt to act as a catalyst?
Yes. Because he's saying there speeds up corrosion.
Yes. But first of all, before you call it a catalyst, you might want to first of all define what a catalyst is, because you might misuse the terminologies that are being used here. You know, mostly catalysts don't change their nature after they speed up the reaction. We are saying they speed up, salt will speed up the reaction because it's a condition. It's more like a condition, not necessarily a catalyst. A catalyst, when you look at catalysis, you discover that the catalyst behaves in a certain way that is different from what is being talked about here. So a salt in this particular case may be looked at as a factor or a condition that will necessitate the increased rate of corrosion due to increase in conductivity. So it's more like it's a condition that is at present, not necessarily a catalyst. But since we are saying it increases conductivity, it may be looked at way, except that a catalyst at the end of the reaction looks different from what the salt might be in this particular case.
Right.
All right. My cursor keeps disappearing. I don't know what's happening. Okay, there it is. So prevention of corrosion. So corrosion can be prevented in so many ways. Some of the ways are general knowledge. Some of it is scientific. And what is important to note is that the processes, here we might just mention them, but later on we might want to interrogate the chemistry behind that prevention process. The reason why we always look up to chemistry to investigate what is really happening is to expose learners to what might be a new discovery from them or an addition to what is already existing. So where there is chemistry, you might want to interrogate the fact. At this level, maybe we might just mention, but as we progress, maybe the second year, third year, we begin to bring in the chemistry. Because remember, the flow of electrons, which is oxidation, it may have something to do with orbital arrangement, and prevention of this corrosion might bring about the alteration in the way electrons are seated in their orbitals or the way they are moving from one energy level to the other. So just take note of such and see exactly what is happening behind the closed doors. So one of the preventive measures, this one is common. So painting, paints prevent contact with air and water. So the main reason here, there isn't much chemistry. It's basically prevention or reducing contact or denying these conditions necessary for corrosion. So examples, you will see cars being painted, gates, roofing sheets. The purpose for painting a vehicle may not necessarily be to beautify it. It could be red, blue, green, yellow, beige, white, khaki, and all sorts of cars that we see on the street. But the real reason behind that is corrosion prevention. Okay, now you know. So the next time someone asks you, what color of the car should I buy for you? Just say anything as long as it doesn't corrode, you know, as long as there's corrosion prevented. Or else you might be driving and the next thing you see, the engine is running faster than your vehicle. It has dismantled due to corrosion. So the main reason is corrosion. Okay, and oiling also, we've seen a lot of oil being used in especially moving parts. Okay, machines, the moving parts of the machines, the tools, and so on and so forth. One reason could be to lubricate for smooth movement, but also to prevent those moving parts from being corroded or eaten away. So what oil does that water will not have access to that metallic surface because the two are immiscible. And I'm using the word immiscible here. One will not dissolve into the other. So especially if you start by putting oil on the metal surface, then water stands no chance. And without water and oxygen, of course, those two being denied access to the surface, there is no corrosion. Another one is galvanization. So to galvanize simply means to coat a metal surface, especially iron in this particular case, with zinc. So zinc is also a metal, okay? But it's not the kind of metal that you would want to use in construction because it doesn't have the strength that iron has. So the main metal is iron because it's strong, it's firm, it can be used in construction. However, it undergoes corrosion. So this iron, when you coat it with zinc, a very thin film on the surface, then you protect iron. Even when the coating is scratched, there could be some parts where the zinc is scratched. As long as most parts are still covered with zinc, there's still going to be protection of that iron. So mostly, water tanks. Okay, go ahead.
On galvanization, are we coating a more reactive metal or is a more reactive metal which coats the less reactive?
Okay, so if you look at your reactivity series, then you'll be able to see that we're using a more reactive metal to galvanize. Okay, so and today most of our roofing sheets, I think they are galvanized, as far as I remember. So you guys can advocate. You being scientists, that let there be law passed in parliament that whoever is selling the roofing sheets, they should be galvanized. I think we used to see some adverts on TV, you know, Wandamalatadumzas galvanized with zinc, this and that, during their advertisement. Most people didn't know what they mean because they didn't explain what galvanization is. Now you know, you can go and spread the word. So it's basically coating iron with zinc, that's galvanization, and your roofing sheets can stay up there for a long time. This is important because roofing sheets are heavily exposed to conditions that are necessary for corrosion. Not just in the rainy season where water is readily available on the roofs, but even just even in a season like this, you find that there will be water dripping from the roofs, moisture will accumulate there, water vapor will condense. So there is always moisture, there is always water there, and oxygen is everywhere. So you can imagine living in a house where you have to change the roof every 2 years. It's not going to be possible. So scientists thought and came up with this process to galvanize your roof so that you don't have to change every now and then. At least you can build. Whoever thinks they're going to benefit from the house, they will discover that they will have to change the roof at some point. So at least they also have to spend. So also have electroplating. A metal is coated with another metal using electrolysis. So there you have it. Science also comes into play. An example is chromium plated taps, also have silver plated spoons or silver plated plates. Okay. Now, the initial idea behind electroplating was purely to prevent corrosion until such a time when unscrupulous people started thinking of scamming people. I'm sure you all know the story of Archimedes, where some characters were scamming the king, creating crowns made of gold, yet they were just electroplating. And he proved that to show by showing the density differences. That actually what was underneath was just a different cheap metal, then they coat with gold. So electroplating can, in this particular case, is a tool or is a method that is used to prevent corrosion. So if you have a silver plate at home, please, you're not a king to be eating on a silver plate. Just check until you discover that what is underneath is iron or even plastic, PVC, and then they have coated it with silver. So it looks like a silver plate. Nothing comes on the silver plate. Silver is very expensive, and it's basically just electroplated. Even that watch, which you think is a gold watch, you can't have gold in Kamwala or Mwinirunga or Katete or Chambori or Magoe or wherever. You can't have gold being sold cheaply. Mostly, it's just a very thin film as a result of electroplating, and they used it for scamming. The whole idea, the original purpose was corrosion prevention, using a metal that is very less reactive, okay, to cover the surface so that what is underneath is protected, because the thin film that is on the surface does not easily corrode, does not easily react with oxygen and water. Okay, alloying is another method of prevention. So mixing of metals to make a corrosion-resistant alloy. An example is steel. Steel is a mixture of iron and other metals. Okay, so the initial steel, they use carbon. Okay, so you learn later on that when they put carbon, when they add carbon to iron, you discover that there's going to be change in the manner in which electrons will behave. Because we have learned that oxidation in this particular case is the losing of electrons. So the addition of these other substances or additions to this particular metal, they alter the arrangement of electrons, they restrict certain movements of electrons, and that prevents oxidation and eventually corrosion. Okay. In this particular case, stainless steel is made of iron, chromium, and nickel. And we've seen some kitchen utensils labeled stainless steel, especially knives. Now, these you can even leave them in the water overnight. Wake up in the morning, you find they are still bright and shiny because the addition of those extra substances or metals alter the chemical nature of iron. So iron is going to be the main metal, but then a small percentage of those other metals such as chromium, nickel, sometimes even just carbon. It depends on what that steel is going to be used for. Is it for utensils, or is it in construction, or is it steel nails, and so on and so forth? Because some of it has to be resistant to bending, some of it has to bend, depending on the use. But mostly those knives, they don't easily bend, they are firm. So they use chromium and nickel to come up with a stainless steel. And that way you can leave your knife in water, go for a holiday, you come back to your room, you discover that that knife is still intact and it's corrosion free. So though this method is a bit expensive, because the alloying itself, it has to come at an expense of extra metals in a certain proportion and using sophisticated equipment to have them mixed thoroughly and uniformly to come up with that metal. However, it is one method that is used in corrosion prevention. We also have cathodic protection. So a more reactive metal is attached to iron. For example, magnesium and zinc and many other metals can be attached to, can be used to be attached to the metal that you want to protect. In this particular case, iron, because we have identified that iron is widely used in construction. So the reactive metal corrodes instead of iron. We call it sacrificial corrosion. So you sacrifice not necessarily a less important metal. Let's call it a less used metal, because you have heavily used iron in very important building. We're talking about maybe a 5-story building here, skyscraper, and so on. And the list that you want to happen is metal that is supporting the frame to corrode and the building collapses. So mostly, especially those metals that have been used in foundation at the bottom or in the ground, they will attach a metal which is more reactive, mostly magnesium or zinc, so that instead of the iron corroding, these metals will corrode, because you don't need a very big piece for sacrificial. As long as the two metals are attached and the electrons are flowing, then that's enough. Okay. If it's depleted, it can still be replaced, so that what has been used in construction remains intact. So an example of cathodic protection here, we have water pipes. So this works by making the metal you want to protect act as the cathode, and an electrochemical cell of an electrochemical cell, so that it does not undergo oxidation. Okay, so you know that oxidation happens at the anode. Okay, So you have to make the metal that you're protecting a cathode. Okay, so how does that happen? You attach to this more reactive metal, which now will act as the anode on behalf of that metal that you're protecting. So that metal you're protecting becomes the cathode, and you know the direction of electrons. So instead of oxidation happening at the metal pipe or the water pipe, as in this example here, we have this water pipe buried underneath. Water passes here, okay? And it is surrounded by soil, which is, the soil mostly is moist. That's why plants are able to survive for a long time, because there is water in the soil. It's moist. So that moist soil acts like an electrolyte, okay? And it's mixed with a lot of salts in the soil that make it act like an electrolyte. So the two metals, the metal of interest would be made to be cathode, and the sacrificial metal here is going to be made an anode. So this will be releasing electrons. Electrons will pass through this connecting wire, which is insulated. It is insulated because you don't want it to have an interaction with the electrolyte, which is the moist soil. So the electrons will be flowing in that direction, and this cathode, this metal of interest, instead of corroding, becoming ion, each time it loses electrons, the electrons are being replaced by the anode, which is magnesium. So magnesium will be losing electrons to this ion. So whenever the ion loses electrons, the ion 2+, instead of reacting with the oxygen to form rust, it quickly receives electrons from this source, which is magnesium. So the magnesium keeps supplying the electrons, keep supplying. And if you look at iron and magnesium, one reason, apart from it being more reactive, the reason that has been chosen that the number of electrons, if this is iron 2, magnesium also releases 2 electrons. So you will see that there is that much in terms of the electrons that are flowing. So you have iron loses 2 electrons. It simply gains, it easily gains from the magnesium that is supplying these electrons. So at the end of the day, this ion remains intact for a long time. So initially they used to have pipes they put there, they corrode, the water starts coming out brown, or the waste happens, the pipes are blocked, and so many other things happen underneath there. So they have to dig them out, they replace them with new ones. Over time, again, the same thing happens until a scientist like you out there came up with this idea and thought of preventing corrosion through electrochemistry by understanding the difference in terms of potential difference and the direction of flow of electrons in relation to the reactivity series of these metals. And eventually they came up with this idea of cathodic protection. So a metal that could have been an anode is turned into a cathode because they add or they attach it using a wire to a more reactive metal that Honorable Francis saying Unza solar system can be the best example. You see, don't go to the office of the Vice Chancellor and start telling him, now we know you didn't galvanize, you didn't cathode protect, you didn't this and that. Anyway, it's good. It's good knowledge. Yeah. So obviously, UNZA was built in 1960 something, 1966. So we're talking about maybe 60 years or so. So you might want to excuse the people that were there at that time. Now it is your time. So let's see what you're going to do about it. That's the beauty of life. After blaming others, then it's your turn. And then we sit and watch. Yeah, we sit and watch what happens. So that's cathodic protection. Now, in cathodic protection, um, just watch out for the metals that are being used, the number of electrons that is flowing, and something might be asked there. But don't worry on how questions come. That's the reason why we have tutorial sheets. So I think there should be a tutorial sheet on acid base, and another one soon will come out, because I think by next week we should be winding up with this topic. So we'll expose you to how some of these questions come. So there you have it. We have corrosion. We look at conditions, factors affecting the rate of corrosion, preventive measures, and the science behind both corrosion and protection of the corrosion. If there are no questions, let's call it a day. It's Friday. Enjoy responsibly and have a good day. Have a good weekend. Thank you very much.
Zikomo.
Thank you.